Okay, excellent. So let's start. So quick recap. Where are we? During the last class, we outlined the plan, which is to understand how to control a system when we do not have a model at hand. So we have some a priori knowledge about our system. We know what the state space is. We know what the action space is, but we don't know how actions turn states into new states. So we don't know the probability transition from states to new states, and we don't know how rewards are given to the agent in response to its actions. And nevertheless, we would like to be able to control the system. So this is the point where we really depart from the classical picture of optimal control, of model-based control. Okay, so this is the part where learning comes in heavily. How do we do that? This for pedagogical purposes, it's good to partition the problem into two parts. The first part is how to learn to predict, and the second part is how to use this prediction for control. This is the same partitioning that is present in the book by Sutton and Barth, so you will sort of find the same conceptual organization that we follow here, except that in these lectures I'm going to provide you a lot more background information about the techniques that are used for this learning part. So we discussed last time that one way of learning the value of a function, that is to obtain from data, from interaction with environment, what is the expected value of a certain policy, given fixed policy. And one possible way is to go to Monte Carlo techniques, which have advantages and disadvantages, as we discussed. But now we wanted to explore something different, and this something different leverages on the notion that the Markovianity of the system allows us to write down recursion relationships for the value function, by which I mean that the value function at a given state is actually connected with the value function at the successive states. And we can use that equation, this linear equation for the value function, in a different way, to solve it in a sense without knowing exactly what the coefficients are, but having access to samples of these coefficients in the form of probabilities, actually empirical probabilities of visiting states. Okay, so so in order to do that, we will consider a problem which is even wider than this, and which is the problem of stochastic approximation. So this will be broader than the problem we have at hand, because we will be able to consider nonlinear equations to be solved by this method, whereas the recursion relation is linear in the value function. So in a sense, it's broader. But for pedagogical purposes, once more, just for the purpose of teaching, we will consider just the one-dimensional case. Okay, so I sort of tried to convince you last time that there is an intuitive interpretation of solving the value function as finding out the zero of a function. So I will get back to that at the end of this part. So we just refresh the connection and see what are the similarities and the differences, if there are. But for now, let's just isolate this problem that we distilled. So from now on, we're going to focus on one particular toy problem, which is, however, everything we need to understand what actually is going on for our system. So what is the toy problem that I'm talking about? Well, it's actually quite simple. It starts with an even simpler problem. Okay. So the first problem is that suppose you have some function in a domain. Okay, so there's an interval of the real axis in general. Okay, so maybe this interval here, and you have a function here. Let's call it this is the x, and there you have a function f of x. And we are interested in finding the zero of this function. So there's a point xi here such that f of xi is equal to 0. Okay, so to warm up, let's first discuss the situation in which f is accessible. Okay, so you can inquire for the value, you can query for the value of this f function. Okay, so the game is the following. So suppose that I act as an oracle. Okay, so I know what the function f is. You can ask me the value of a function at any given point. Okay, so if you prompt me with a request, give me the value of the function at a certain point x node, I will return you the value of that function. Okay, so you don't need to know the full form of this function. You just need to know that I can return you the value of that function. Okay, so given this kind of information, this kind of exchange of information between you and me, and again, if you want to focus in terms of learning, you are the agent who is trying to learn, and I am the environment which is providing you the data. Okay, and f is something which is related to the environment. We will see then the connection with the value function later. But the game is the following one. Okay, so this is the order -1 problem. Okay, so you see I'm not even introducing anything stochastic here. Okay, so how would you solve that problem? So since I want you to wake up quite early today, I'm going to ask you this question. So can you come up with simple ideas, simple algorithms that solve these problems? How to find this 0 here, given that you can do the actions that I described previously. So you can ask me the value of a function, of this function at any point. But that's all you can have. That's a lot. That's a lot of information. So how would you suggest to proceed?
We can use something like the dichotomy algorithm. It's like you take 2 far points, and then you ask what is the value of the function. Then if it is positive and negative, you reduce your interval and so on.
Excellent. So this is the dichotomic approach, which works well if you are in one dimension, which is fair because I told you we're working in one dimension. But you should always keep in the back of your mind that eventually we're going to move this to any dimensions. So
sorry.
Yeah.
Can I ask you what the assumption again about the function? If we know anything, or is just
yeah, right. You're right. So I was just introducing very loosely the idea. So the function, you can assume it that is decreasing, like I plotted it. It has to be monotone, but let's fix the ideas on which it's decreasing, and its derivative is everywhere strictly negative. Okay, so it's not just like it becomes flat at some point. So it's what you would expect in case you just have 1 0. Okay, the kind of conditions that allows you the problem to have just a single 0 in your interval of interest. Is that what you were asking for?
Yes.
Do you want me to write? I mean, we can write the conditions here. So the conditions are that f prime of x is strictly bounded by some minus g with capital G positive. Okay. So it means that if I take the slope of this, it never becomes flat. Okay. It's always going down by some finite amount. And this is enough to guarantee you that there is a single 0 in the interval of interest.
Okay, then I would ask you 2 points and start to guess what the gradient is in order to move toward that direction.
Okay, right. So one possibility is to ask the gradient, but I told you this is not in the rules. I can give you the value of the function.
Yes, of course, but then I can approximate it with the...
This is one possibility. Okay, you can ask me the value of at one point and the value of the neighboring point, and we can compute the gradient of that. But there's something simpler.
Well, if the gradient, if the derivative is negative, we can just move into that direction until we hit 0 or go below it and then go back, basically. Okay,
sort of approaching this. Can can you just elaborate a little bit, because there was a lot in that sentence? So how would it work? So let's take a step. So suppose we start with x equals 0. Sorry, x equal x naught. Then I give you the value of the function here. So what you would do next?
Well, I could just take the value there. Then I don't know which is the direction of the, if it's increasing or it's decreasing. So I just move in one direction and then I see if the value is higher or lower.
Let's say the function is decreasing, like we said here. It's going down like this one.
Okay, then I would just see which is the current value, and then I would move ahead of one step, say, and see if I am still over or below 0. And if I'm over, I still go. So if it's still positive, I maybe accelerate. I could accelerate, or just say that I go ahead by one step because we want.
Okay. We are approaching the point where I wanted to get.
So I basically march down until I hit ground level.
Okay. Yeah. That's probably the simplest algorithm, which I'm going to write down in a more obvious form, if you wish, which allows us to fix the ideas about exactly how to implement it. So the idea would be your next guess for the point x, sorry, for the point x at say step k plus 1 is the point x at step k plus some parameter alpha, which we're gonna fix in a second, or discuss at least, and then the value of the function in that point that you sampled. Okay, so you see how the game works. So you choose a point xk starting with k equals 0. I give you the value of the function. Okay, then if the function is positive, this means that you have to step to the right. If the function is negative, it means that you have to step to the left. Okay, and this alpha here, which goes on the different names, step size, but we're going to call it the learning rate. Okay, so do you agree on what this algorithm is doing? So x naught, compute f of x naught here. It's positive, so we're going to take a step in this direction, which is equal to the value of the function times the parameter alpha. Clearly, as we approach the 0, the steps will become smaller because the value of the function becomes smaller. Okay, so in this case, you can prove that this algorithm approaches exponentially the zeros. Okay, it's a very simple algorithm. It doesn't require to compute derivatives or to approximate them. It's just a way to approach the 0. Okay, so so far so good. And now this is a good point to make an important connection with something you might be familiar with. And the connection comes here. Just suppose we assume now that our f function, okay, so this is a remark. Suppose that our f function is actually the derivative of another function. Okay, so what does it mean in terms of the function capital F? Well, the function capital F is clearly, you see, the derivative of the function capital F here is positive here. It's 0 at this point xi and goes down after. So if I have to plot the function capital F, it's going to be something like this. This is my capital F of x. So in this condition here becomes the second derivative of x strictly negative. Okay. So, and what does this algorithm becomes? Well, small f is f prime. So for my capital F function, the algorithm becomes xk plus 1 equals xk plus alpha f prime in xk. But this is gradient descent, gradient ascent, sorry, because we're looking for the maximum. Okay, so this problem of finding a zero is just a broader perspective on gradient ascent, if you wish. It includes gradient ascent in itself. But it also considers other kinds of problems, which are not necessarily gradients, okay? Because in many dimensions, you can ask the zero of a set of functions, the solution of a set of equations, but not necessarily these equations are gradients of a potential function, okay? There might be just vectors which are no gradients at all. So it's a broader question which encompasses also the problem of gradient ascent, okay? So you see that this algorithm of finding zeros is basically a gradient ascent in disguise. In one dimension, the two things are indistinguishable because every function is a gradient of another function. Okay. Everything clear so far? Good. Then we have to move to another problem, which is the one that interests to us. And the problem, I'm going to formulate it as follows. We're going to go by the same rules almost, in the sense that you can ask me for the value of the function at any given point, but what you will get in return is a noisy version of that function. So it's the true function plus some noise. And the distribution of this noise, you don't know. Okay? So what it amounts to be is that now we are playing the game by which if you ask me the value of the function at x node, I will not return you the point that you see here in the middle, but I will return you something like a point here, or maybe a point here, or here, or here, depending on the time that you ask me the question or whatever. Okay? So we will make that some technical assumptions on what this noise is. But the question is always the same. If I return you noisy estimates of the value function, will you be able to find the zero also in this case? No. Idris says no. Okay, I'm going to show you that you can.
You can
because
if you if the algorithm learns from the previous value.
Sorry.
The problem is,
yeah, just one at a time. So let's hear from Idris first, and then Aya, just a second, please.
no, because you said you don't know the distribution of the noise. So,
and I will show you that you don't need that.
Okay.
Okay.
We are lucky then.
Okay. Aya, what were you saying? Sorry.
I was saying if we learn from the value, if we estimate the value, and if it's near the real value, then we can account for the noise.
Okay, that's what we hope for, but we will see that it does not always work. So both of you are right, okay, in the sense that it's not always working. It's working sometimes, but you don't need to know what the noise is, okay? So we're going to find a way, the conditions under which this kind of algorithms can work. So, and the basic idea is that in fact, we would like to use the same kind of algorithm as here, but now replacing the true values of the functions with their noisy estimates. Okay, so if we go back to this the interpretation in terms of these terms, what we're trying to do, the equivalent is stochastic gradient descent. So, okay, we're gonna do the same thing. It's just like climbing a function with noisy estimates of the gradients. Here we want to find the zero of a function with noisy estimates of the function itself. Okay, is the layout clear to everybody? Do you have questions before we dive into the math?
Yeah, question is, we can get close to, or we actually can get the
Very good.
optimal.
Excellent. So we're going to show today that we get to the zero with probability 1, which is the best you can do in a stochastic setting. So this means arbitrary close.
Okay, thank
As you will see that, so we can sort of have an informal discussion already. before we put the math into. So what kind of problem could arise when there is noise if we try to apply the same kind of algorithm as here, okay? So we are trying to use this algorithm, again, replacing noisy estimates. So just like using this plus some noise at step K, which I'm not going to specify its properties so far, but let's say just it behaves well, okay, in the sense that it has a zero mean and finite variance, but whatever else, I don't care, okay? I will also assume that it has some technical properties like the Martingale property, so okay, whatever. But let's say it's a reasonable choice for the noise. That need not be Gaussian, not be anything, okay? All the rest is left to the environment to choose, to decide. So what can go wrong with an algorithm like that? Okay, so remember, there are two things that we have to do. So first, we start somewhere. We don't know where the zero is. So we start here, or we could start in any other point of our interval, which could be the full real interval if we have a function which is everywhere decreasing. And for instance, in our value problem, since the problem is linear, the domain of the function is infinite. Okay. So the first thing that we have to do with this algorithm is to get close to zero as fast as we can. Okay. So if we start very far away on the left, somewhere here, okay, so we would like to take large steps to get close to zero, which is one thing that we want to do. But when we take large steps and there is noise, then something nasty could happen when we are close to zero, okay, because we might start flipping from one side to the other. And since there is always noise, we are never arbitrarily close to the point, okay? So you see that when there is noise, there is some tension between having large learning steps and small learning steps. So in anticipation to what we will show later, this algorithm can be made to work if you choose appropriately your learning rate. Okay, so this will become the key ingredient. The same algorithm that we can use for the deterministic situation where I give you the true value of the function without noise can be applied in the presence of noise if we carefully control the learning rates in a way that I will make clear, hopefully soon. Okay, any additional question before we start? Okay, you can stop me at any time if anything becomes fuzzy or unclear. All right, so now we are ready to state, let's restate the problem in a more formal setting, okay? So I'm going to repeat some of the assumptions that I'm making. So I have a function f in some domain, in D, and this is an interval of the real axis for us. And my function f prime of x is everywhere more negative than some minus g, with g positive. And there is, therefore, in this, I'm setting myself in the conditions where, of course, at the two extremes, the function is positive on one side and negative on one side. So I'm assured that there is a point xi such that f xi is equal to 0. And this condition on the derivative tells me that this point is a unique. Okay, so there is 1, 0. So basically, I'm just restating what I pictorially draw here. This is my underlying f, but f itself is not observable. What we can observe is, in fact, a random variable phi, such that the expected value of this random variable phi at point x is f of x. Okay, so this means that this phi here is an unbiased estimate of f at x at any point, okay? Which is another way of writing that this what I get, my phi, if you wish, informally. Phi at x is f of x plus some noise eta, where this eta has zero mean and finite variance is less than some, I don't know, some constant of which I don't want to use the names that I'm going to use in the following. So let's call it capital C, whatever. Okay. So this is all I'm asking at the moment. This unbiasedness condition can be relaxed, okay, but we're not going to do it because the calculation becomes even heavier than they are. So if it's slightly unbiased or asymptotically unbiased, all the calculation will work as well. But we will ignore this this part for our class. Okay. So the statement, so that I'm going to prove later. So the statement is that the sequence of points generated by the algorithm x k plus 1 equals to xk plus alpha k times phi evaluated at the point xk. Okay. So this means the random estimate of my function f at the point x. This is what the oracle, that is myself or the environment, will return to you if you ask for it. Okay. So you see that now I've inserted, this is the key ingredient, I've inserted a dependence on the time step or the iteration step of the learning rate. And we are going to play heavily on this. Okay.
Professor, I'm a little confused between the difference between gradient descent and stochastic gradient descent.
Well,
what is the stochastic part?
The stochastic part is that here your gradient descent, if you had the estimates, stochastic estimates for the gradient, so if you replace this term here with the f prime of x plus noise, this would be stochastic gradient descent.
Okay, okay, thank you.
Sure. Okay. At a very superficial level, but that's the substance of the thing. Okay. All right. So as you will see, I'm introducing a dependence of the learning rate from the time step, which qualitatively speaking, and we will see how this plays out, means that what I would like to do is to have large steps at the beginning, when I'm possibly very far away from my target point psi. And as I approach it, that is, as the number of iteration increases, I would like to reduce these steps in order to kill the noise. Okay, so there is here, and we will make it explicit in the end, there is a bias variance trade-off in this problem. At the beginning, we want to remove the bias, and the bias comes from the fact that we have to start somewhere. We have to make some assumptions about where our zero is. That is, we guess some x node at the beginning. Okay? This is my initialization here is choose x node in D. And in general, you might have no information, you may start somewhere, or you might have a guess. But anyway, any choice introduces some bias at the beginning. And you want to remove this bias, that is, you want to approach the zero, but you also want to keep the variance under control. And this is accomplished by scheduling the learning rates. So these learning steps or rates are scheduled in time. This is a technical jargon in the sense that we are going to find some dependence on time on the iteration step that accomplishes this delicate balance, well, actually not so bad, delicate, it's quite robust balance between bias and trade-off, bias and variance, sorry, trade-off between bias and variance. Okay, so I'm going to make the statement now, and the statement is that the right way to choose these learning rates is to ask that the series with k going from 0 to infinity of this alpha k diverges, and the series from 0 to infinity of alpha k squared converges. Okay, so if these two conditions are sufficient, okay, these are sufficient conditions for what? This implies that my sequence of points xk for k tending to infinity converges to psi, my zero, with probability 1. Okay, so that's the mathematical statements of stochastic approximation. You have an algorithm, which, by the way, is called the Robbins-Monroe algorithm. These are two persons, Robbins and Monroe. And the paper is from 1951. Okay, so it's something that, just to put everything historically in perspective, Bellman was working at optimization problems at the same time as when Robbins and Monroe were working at stochastic approximation. Then the two things merged much later on, okay, merged in the 80s, 90s. But these two objects were well known much before that. Okay, so is the statement clear? We have an algorithm, we have conditions on these learning rates, and we want to prove that this sequence of points converges almost surely to our zero. Fine. So,
sorry.
Yeah, please.
Can I make a question? I didn't understand why doing small steps reduce our variance in the near of the zero of the function. Okay. Because if the error has a high variance, we always have the output given by our oracle is noisy, is wrong. Also, if we do small steps.
Okay, fine. But what happens is that so let's have a look at what is happening here when you approach the zero. When you get close to here to our so let's zoom on this area somewhere here and see what happens. So this is your true function, which you don't know, and then you're here around and you get some estimate here. Okay, now if your alpha is large, you will step very likely we will make a step across the zero. Okay, and you will get some estimate here. For instance, here it may well happen that since your distribution is as a finite variance, you might as well get a positive value for your random estimate, even if you are on the right. Okay, this may happen, and if this happens, this is going to push you farther away from the point. Okay, so how do you deal with this kind of problems? So now suppose that you make very small steps. If you make very small steps, this means that from one time to another, you're not moving much. So you're sampling in a point which is very close, and therefore your variance is reducing, and therefore after many trials, you can be reasonably sure that your value here will be negative. Okay, so you see, if you don't move much, you can kill effectively your variance, but if you move a lot, then it's going to be a problem. Okay, so just like when you want to take a photo, you have to stand very still, and if you try to take a photo when you move, it's complicated, right? That's sort of analogy. Is that any clearer?
Okay, so is a sort of that if we continue to sample that particular point, in the end, by giving a sample and sample, we reach the real value.
Yeah, exactly. So
okay.
I mean, if you don't move, if you ask me 100 times the value of the function at the same point, you're going to kill the variance very effectively, right? And this would mean that you, but however, you're not making any step, like just like having alpha 0 here. If you ask me repeated many times this. So this is very good from the viewpoint of killing the variance, but it's very bad from the viewpoint of killing the bias, that is to moving towards 0. On the contrary, if your alpha is large, this is very good if you want to move away from 0. But the point is that the variance is not killed as effectively. So you have to find the right balance. Is that any clearer now?
Yes, thanks.
Sure, no problem. Okay, very good. So before we start, just a first another clarification, if you wish. You might ask, these two conditions I mean, how hard are they to be satisfied? Okay, so is there even a way to fulfill them? Okay, and actually, in fact, it's not particularly difficult to satisfy these conditions. The only thing that you have to require is, for example, any sequence of alpha k, which for large k, for k tending to infinity, behaves like k to the minus some exponent beta, say beta, with beta comprised between strictly comprised between 1/2 and 1. Okay, this satisfies these two conditions. Okay, for anything that is in that range, so that asymptotically behaves like a decaying power law with that exponent comprised between 1/2 and 2, you can easily check that these conditions are satisfied because the series above diverges and the series below converges. Okay, so this is not something that it's very difficult to achieve, and actually there are very many ways of achieving this property, so it's not particularly restrictive. But remember that these are sufficient conditions. Okay, so you might have problems in which you can find schedules that are outside this range and for which your problem works as well. Okay, so I hope we managed to get to the point where I can give you examples, but if it's not the case, bear in mind that these are sufficient conditions but not necessary. Okay, so there might be other choices that we do not include, but nevertheless these are wide enough. Yeah, please. I see.
Sorry.
I have another observation, but go ahead. Maybe one at a time.
Okay, yes, please. Andrea, then...
No, just quickly, can we go through again the assumptions, the hypothesis of the theorem?
Sorry, I didn't get you.
Can we see again a second the conditions of the theorem?
This ones?
The assumptions on F and no.
All right. Yep. Which one are you concerned about?
Okay, so we need. Sorry, no, though I missed that detail. We don't need anything in particular about the distribution of the noise.
No.
We just require that the function is derivable. Is that correct?
The actual function must be differentiable, yeah.
And with bounded derivative.
And with bounded derivative,
okay.
Yeah.
Thank you. Sorry.
No problem. Please.
Yeah, I had another observation. I was thinking, basically, since we have noisy estimates of F, we are never going to be able to overcome that uncertainty in locating the zero, basically. Is that correct? I mean, we can never get more precise than what eta allows us to get.
Well, my point is exactly that by properly choosing the learning rates, you can actually overcome the noise asymptotically. So for large number of iterations, and eventually that's exactly the statement, that you converge to the true zero with probability 1. Okay.
No, because what I was thinking was, if we know that if we can have some assumption, as is in this case about noise, like that it has a fixed variance, So basically, we always get a noisy estimate with the same maximum error from the actual point.
We're going to use this. I mean, we're going to use the fact that the variance is bounded.
Okay. So basically, we know that wherever we are, if we ask enough time to the oracle an estimation for the same point, eventually we're going to figure out what the variance is, and so we are going to know how far we may expect to be from the actual zero.
This is guaranteed, only that this is a poor way of finding the zero, in the sense that you spend a lot of time in the same point and you don't move fast enough. Okay.
Yeah, but no, what I was thinking was maybe it's just a thought experiment, that maybe we can do this process of estimating the variance anywhere, so it doesn't matter where we are.
Very good, very good, very good. This allows me, yes, let me just barge in, and because this gives me the opportunity to discuss one thing that I want to skip over, but now since you ask, you could have solved this problem another way, okay, which is, for instance, you choose a certain set of points, the yellow points here, okay, and you sorry, this must be they must be in the domain, and you repeatedly ask me for, I don't know, 100 estimates in this point here, okay? So you will have a cloud of this, and you will have a cloud of this. And then from this, since you have 100 points, you say, okay, my error is going to be 1% around this value of the function, right? And so I could sort of construct an approximation by uniformly sampling my domain, and then trying to draw the line and the intercept and go about like this. Is that anything close to what you have in mind?
Yeah, basically what I was thinking is something like this, like maybe before even starting to move, so at the beginning of the algorithm, I don't move at all. I just ask where for the current position to the oracle. So I get an idea of what is my interval of uncertainty. And then once I have this estimate, so basically I know an interval, how big is the interval of my positioning in the space, then only once I have an estimate of this error that I am enough confident with, then I start moving without, well, taking into account this error, but anytime, I don't know, I move the center of the interval, basically.
It's crystal clear for me. I think it's also clear to all the other. And but what you're actually doing here is explore then commit. So you're gonna do all the part of exploration first, and then you're gonna go down your approximated gradient.
Yeah, it's basically I'm turning the knob completely toward the exploration at the beginning without moving at all, just looking around and then going for pure exploiting.
And now I will give you two reasons for why this is a loser's strategy. The first one is that if you live in many dimensions, this attempt at covering the space is hopeless.
Yeah, sure.
First. Second point, if you do not adapt the grid over which you are looking at your function, at some point when you get close to the zero, okay, you will be in a situation where there is a shortage of information because your 2 points will be wide apart, and here in the middle you cannot overcome the noise, so you will need to sample more and more close to zero. Do you agree with that?
Yeah.
So the reason why we do this algorithm is exactly for these two reasons. First, because it allows to search rather than to sample first. Okay, so you sample only the points that you need for search, which is again one instantiation of the balance between exploration and exploitation. And second is that you do that adaptively in a relatively stupid way, admittedly, because you adapt only with respect to the number of steps and not with respect to the value of the function. So there are better ways of doing this, but still this is a way in which you sample differently depending on where you are. Whereas in the approach that you suggest, that, I mean, it's perfectly honest at the beginning, you don't do that. So you see the shortcomings.
Yeah, okay, I think I understand, yes.
Okay, great. Very good. That's all excellent. So I see you're live, but we have to start with the math for real now, okay? So let's do it. Okay, so I think this is going to take us sort of some 10 to 15 minutes, but we can slow it down to 0 almost if you get stuck anywhere. It's not going to be very, very complicated, right? So bear with me. So we're going to sort of give a proof in a sense of mathematically reasonable but not fully rigorous theorem-based setting. Okay, but it's proper. Okay, so first of all, we want to show that this holds with probability 1. Okay, now checking that the probability of a sequence is close to 1, it's very difficult to state mathematically. So luckily enough, there is some other condition which is stronger than probability 1 and therefore implies probability 1. So what we are actually going to show is that if we consider the expectation of x, say n, I'm going to switch between k and n, doesn't matter, it's just one step of my algorithm, minus 0 squared. If this expectation goes to 0 as n goes to infinity, this implies that xn goes to psi with probability 1. Do you agree with that? So if the points, if the mean square error, which is this object, between the true 0 and my estimate of 0 goes to 0, it's impossible that there is any probability left outside that. Okay, you can prove this by contradiction, in the sense that if there is some probability that my xn, finite probability that my xn eventually is not psi, then the mean square error cannot be 0. Okay. If I don't hear any objection, I think that this is you're gonna buy this, and you should. So what we're gonna focus on is this statement, which in turn will imply that fact that probability with probability 1 we converge to that. And the way we're gonna prove this is by means of a relatively brutal calculation. Okay. So the way this calculation goes, so let me call this the proof, because I don't want ever to have a mathematician looking at this video and insulting me for having called this a proper proof. But it's a sort of argument that captures quite closely all the necessary steps. So the way we go is just we take the expectation value at step n plus 1 minus psi. Okay, so this is the same object as before, just one step after. And we are going to use now here, by definition of the algorithm, I'm going to replace this object here. Okay, so I'm going to put inside this exactly this expectation here. So this is just by definition, it's equal to the expectation of xn minus psi, and then I have plus alpha n phi, which is my random estimate of the function, all of this squared. Been doing nothing here, just replacing the definition of the new step in the previous step. And now, again, doing very little, I'm going to just unpack the square and trying to get at the square of this difference at the previous time and all the other terms. Okay, so I'm just expanding. Again, nothing serious is happening here. And then I have twice alpha n. So alpha n is a number, a positive real number, so it goes out of the expectation value. There's nothing random here. Expectation of what? Of the product of these two, which is xn minus psi times phi of xn. And then I have the last term, which is alpha n squared and the expectation of phi of xn squared. Okay, so far so good. So let's recall, what does this expectation mean? So what is random here? Remember, every time that you pick a value of x, I will return you a stochastic estimate. Okay, so this expectation is over all the randomness that is there, over all the sequence of noises at all times. So at step n minus n plus 1, there have been n plus 1 noises before that contribute to this expectation. Okay, very good. Now we're going to do something for real here, which is the following one. Let's focus on the middle term. Okay, so I'm going to highlight this middle term here. And we're going to work this out a little bit. So this this expectation of this product. So what is it? So remember that this term here is the value of the function xn plus the noise, which we have evaluated at step n. This is the noise term. But this noise, okay, it's something that is fresh, at every time is refreshed. Okay, so it doesn't depend on the actual xn that you choose. It's something which is up. This is the Martingale property that I was talking about at the beginning, which is technical, but means basically you can replace it by the assumption that noises are independent at every draw. Okay, so if noises are independent at every draw, this estimates. This means that the part here is totally independent of the noise which is present here. So I can expand this and take the averages, and remember that the average of the noise is 0 because phi is unbiased. So this object, I can actually replace it by the expectation of xn minus xi times f of xn. So I averaged out the last noise. There still is an expectation because this point xn depends on all the previous noises that I had. Okay, so I am there because I had a sequence of noises which affect my algorithm, and therefore there's still some average to be done. But I just averaged out the last noise that I've seen. Okay, now I'm going to work a little bit more on this term, and I'm just going to do a very, very simple manipulation, which is I'm going to write this as xn minus psi squared f of xn divided by xn minus psi. Okay, here you should be sort of kind of alert because I'm dividing by something which could be 0. Okay, so this might be potentially dangerous, but of course, I mean, this happens with probability 0, that you are actually on top of your 0. Okay, at every step of the algorithm, the probability of falling exactly on a real number, this happens with probability 0. So this term is divergent with probability 0. Okay. So we shouldn't be particularly worried about this. But again, this is sort of a patchy. This is where the physicist comes in and does the bad mathematical stuff. But you can fix this properly mathematically, but just stay with me, okay? Good. Now, why do we want to do this? Well, because this object here that I have here, this ratio, well, what is it? If I go back to my picture above, this is no, I'm going to redraw this because it's going to be a mess. So let's redraw this object here. So remember, the function has always a derivative like this. So for every point xn, this is my value f of xn this is psi. Okay, so this ratio here between the value of the function and the separation here is a negative object. It's always negative, because if I am on the left, f is positive, but the distance xn minus psi is negative. On the other hand, if I'm on the right, my f is negative and my xn over n is my xn minus psi is positive. Okay, so this object here is always strictly less than 0. And in fact, because of the condition that f prime of x is everywhere smaller than minus g, sorry, you cannot read this, so let me erase. In fact, you can make a stronger statement, because the condition that f prime of x is strictly smaller than minus g implies that f of x divided by x minus psi is also smaller than minus g for all points in D. This is just, you may think of this object as a discrete derivative, and this is necessarily bounded by the true derivative. Okay, again, this will require a couple of passages to be proven mathematically, but the intuition is quite obvious. If the curve cannot be steeper than something, then any finite difference cannot be steeper than that. So why do we use that? Because this allows us to say that this term is in fact not only strictly smaller than 0, but is actually smaller than minus g, which in turn is smaller than 0. So we can bound it. And if I combine all this together, this means that this average here is also smaller or equal than capital G, which is positive, remember. It's the modulus of the derivative, maximum derivative. This is more than the expectation of xn minus psi squared. And that's it. Yeah. Okay. So why did I want to do this? Well, because by this technique, I got rid of the phi, which is in the middle. I got back to something which is of the same kind as the first term. Okay, so I'm trying to boil everything down in terms of these mean square errors, so that I can have some recursion and use it to prove that these mean square errors are actually going to 0. I hope you are with me still. Okay, so let's plug back in this inequality in orange or yellow. Let's plug that back in here. Okay, so we restart from here. Let's call this equation 1. And we begin again from this, which means that if I rewrite it, the left-hand side is this one, which is then smaller. So this object here is going to be less equal than a term on the right-hand side, which is explicitly this object is going to be smaller equal. And this is just taking it. This part was the exact one. Then I have my inequality, which tells me that this is minus 2 times g e of xn minus psi squared. And then I have another term, which is plus, sorry, there was an alpha n here. And then I have an alpha n squared, the expectation of phi of xn squared. Okay, so first part done. Now second, we're going to now take, sorry, we're now going to take care of this term here. So this object here is it's the square of my estimate. Okay, but the the expected value of a square is the expected value of the function squared plus the variance of the function itself. Okay, just the second moment is just the first moment squared plus the variance. And now both of these things are bounded, okay, because my function here is finite over all the domain. This is my f of xn squared, which is bounded. This object is bounded by hypothesis. This one is bounded. So I can say that this term overall is smaller or equal than some capital H. Okay, this is just a consequence of the finiteness of the mean and the variance of my estimates, as it should. Are you okay with this? Fine. If we can do that, then we can add another step to our inequality. So this is my equation 2. And then if I take it back from 2, I get that further inequality, which is less equal. Sorry, let's rewrite this again for clarity. This is expectation of xn plus 1 minus psi squared. Let's equal then the expectation of xn minus psi squared minus 2g alpha n expectation of xn minus psi squared, and I'm copying so far, and then I add the last step, which is plus alpha n squared h. Okay, so far so good. We have a few steps left. So do you want to take a break here, or do you want us to go through? It will take at least some 5 minutes more. Do you want to take it right now? Okay,
I think let's finish.
Let's do it.
I prefer to finish, yeah.
Okay, let's go. Let's go. Good. Fine. So the next step is that what we're going to do is something quite simple first. So let me do it online, that is without rewriting the formula. What I'm going to do is just I'm going to move this term here to the left-hand side. Okay. So which means that I'm going to do it in a way that I hope you will tolerate. It's just that I put a minus here and then I get it this. Okay, have you seen what has happened? Nothing serious. I just moved this on the other side. And why do I want to do that? Because this terms becomes the difference of the two mean square errors at two consecutive steps. So what I'm going to do now is I'm going to take a sum. So your sum n from 0 to some I don't know, capital N. Okay, so I'm going to take the sum of both sides from the starting point to some point n, capital N. Okay, or maybe capital N, yeah, capital N. Yeah, right. So why do I want to do that? Because the sum will be a telescopic sum. Okay, so when I sum the differences, all the terms in the middle will go away, and I will be left just with the last and the first term in the sum. So this means sum with n going from 0 to n on both sides of the inequality. Okay, so like I said, if I do the telescopic sum on the left-hand side, what I get is the expectation of x capital M plus 1 minus psi squared minus the expectation of x0 minus psi squared is less equal than, and then here I have to do nothing but to rewrite the sums. So this is going to be minus 2g sum from 0 to capital N of alpha n expectation of xn psi squared plus h sum and going from 0 to infinity of alpha n squared. Okay, and now you see where is the first point where our assumptions start to matter. Okay, because
sorry, isn't that a capital N? The infinity.
Yeah, you're totally right.
Oh, right. Okay.
I was stepping ahead. It's not time yet to take the limits. Thank you.
Sure.
Okay, excellent. So, but you can also have an insight on why we asked that initial condition here, the condition on the convergence of the sum of the alpha squared. Okay, because this will allow us to make this term on the right meaningful. Because if it were diverging, then we would have a trivial inequality, something less than infinity, which we really don't care about. Okay, so this is just to give you a sense where these conditions emerge naturally from this kind of computation. Very good. So very, very few steps now, just a couple of them. I think we're in good shape. And what we have just to do now is just to rearrange this sum a little bit. So what I'm going to do is I'm going to take this second term here. Yes, is that one we need to do? Just a sec. So I check that everything is in place. Because if I make a mistake now, it's going to turn out to be a mess. Yeah, that's fine. Yeah, right. Good. So what we're going to do now is we're going to take this bit here, and we're going to move it to the left-hand side. So this is just, again, a little bit of rewriting with shuffling, nothing serious. But I also divide by this 2g, okay? So let's write it, and then if you don't see it, you can complain openly. Then this is smaller than 1 over 2g times what was on the left-hand side that now goes on the right-hand side with the minus. So this is going to be okay. And I have still this plus h sum from 0 to n of alpha n squared. Okay, so this is a minimal rearrangement, just taking one thing on the other side and dividing by everything by 2g, which is positive strictly. Any question?
Sure. No, there also is the 1 over 2g for the h. Should be.
Thank you. Right. Very good. Now, this term here, this object is positive, okay? So, and there's a minus in front of it. So we can further bound this object. So we can remove it from the inequality and further bound it by using 1 over 2g, expectation of x naught minus psi squared plus h over 2g sum from 0 to n of alpha n squared. Okay. And now we are done, essentially, because now we just have to think and to use our hypothesis. So remember, our second hypothesis was convergence of this object. Okay, so this in the limit, when we take the limit of n going to infinity, this object here converges. Okay, so basically this means that all this term on the right hand side is bounded from above, cannot go to infinity. But let's look at what we have on the left hand side. Okay, so the comparison here is between what we have on the left hand side. For God's sake, what is happening? I'm trying to, okay. Okay, I have it there. Sorry. So we have this on the left hand side, and we have this on the right hand side. And by my hypothesis, okay, everything that is on the right hand side must be smaller than some other constant capital M because of convergence of the series. Okay, so for any capital N, the series, this is a series of positive numbers. So if it converges, there must be an upper bound to it. And this first term is just how far I am from my initial point. Okay. So the only condition here I have to impose is that I don't start infinitely far away from my zero. If my interval is finite, this is fine as well. Okay. So this will be bounded by two terms. One is the sum of learning rates, and the other one is how far I am from the origin, from the zero. Okay. But if this is bounded, okay, now I use my second hypothesis, which is sum over alpha n going from 0 to infinity, diverges. Now, if my sum of the learning steps diverges, it's not possible that this term here to be finite. This cannot be finite, because if it were finite in the limit, the left-hand side would diverge as well. Okay, so this term, this implies that the expectation value of xm minus psi squared must go to 0. You see, I have something which is finite on the right, and I have a series of terms on the left, which has one part here that doesn't go down fast enough because it will diverge in the sum. So if by contradiction, if you assume that this term here, this mean square error, goes to a finite value, this will mean that the left-hand side is infinite. So it doesn't clock. Okay? These things cannot work unless this condition is met. And this implies xm going to psi with probability 1. Okay. So this is the essence of the mathematics. Now we take the well-deserved break and we think about what we actually been doing for real with this demonstration, with this proof. Okay. So I think we can start again at 25.
Okay, thank you.
See you later. Okay, back we are. So let's try to wrap it up in this remaining half an hour that we have, because we have to sort of complete our understanding of what we have done, move to the multidimensional case, and then revert back to the value function. Okay, so it's going to be a ride through these different concepts. But the first thing is that when we try to realize what this algorithm is actually accomplishing, okay, so the statement is we have sort of proven that stochastic approximation converges with probability 1 to the 0 of the function, which means that we have also proven that in one dimension, stochastic gradient descent converges with probability 1 to the maximum of a concave function, okay, given the scheduling of the rates that we have chosen. So before going to the multidimensional case, let's first discuss very quickly what is actually happening. So this is a sort of just a remark. So first remark, let's consider a slightly different situation in which we have the number of steps, capital N, is fixed a priori. So it's a slightly different version of the algorithm in which you don't go on forever until you are close enough to your zero, but you say, I have a budget of iterations to do, and I want to keep that fixed, capital N. And then we use alpha also fixed. Okay, so we are no scheduling here. So it's clear that this is not going to have exactly the same performance as the other case, because we cannot go on forever and we cannot get it down. But we can repeat the calculations as we did now, which are slightly simpler. And the bottom line is that if we repeat the calculations, which I think is also a good exercise to do before getting back to the proof of the theorem, because everything is more straightforward and then you understand the little subtleties. But if you repeat it, what you get is that the sum n going from 0 to capital N of the expectations of the squares is less equal than the expectation of the initial point squared divided by 2g plus h over 2g. There is a half alpha here, there is an n here. Okay. So this is exactly the same kind of calculation as above, only that now since the alphas are constant, they get out of the sums, and then everything is simpler. So this object here, what is it? So this is the cumulative error, okay, squared error. So at every step, if you are away from your zero by xn minus xi, then you square it and you average it and you sum. It's a measure of the regret of your algorithm. So how many errors you have accumulated over time. And what this calculation is telling you, that this object is bounded by two other objects. Okay, so this first object here is related to the initial guess. Okay, so this is bounded, if you wish, by the width of the interval, the size of the interval squared divided by the gradient and alpha. Okay. So this is the term which is sensitive to the initial bias. So the closer your guess is to the actual zero, the smaller this term will be. Okay, and you see that this term features the learning rate at the denominator, which means that if you want to make this term smaller, the first term small, which you should do, because if you make the right hand side small, this means that also your left hand side is small. So your regret, the cumulative error of your algorithm is small, which is something that you would like to have. But in order to make this first term small, you would like to have a good guess, which makes the numerator small, and the large alpha, a large learning step, because this will make you run closer to the zero faster. Okay. This second term here, on the contrary, it features basically the variance here. Okay, this term depends on the variance of your noise. So if you want to make this term small, well, one way is just to know that if your estimates are very good, the variance will be small, okay? But this doesn't depend on you. You get the variance that you get. What you can get here is that you can reduce alpha. Having small alpha means that you're making many steps close to each other. So you're reducing the error due to the variance. But of course, this depends on the number of times that you make it. So here there is, sorry, this is not small n, it's capital N. Okay. So you see, this is essentially what these algorithms are trying to achieve, to balance the initial bias and the variance, the cumulative error due to variance, together. And in this particular case, if you keep a fixed alpha, then you realize that there is an optimum choice for alpha. And this optimal alpha is, I mean, you can derive it. I don't know if I have it here. I don't want to mess up with the, okay, but you can derive it. It's the optimal alpha goes like essentially, okay, I can do that. It's going to be n to the power 1/2. And here you have on top of the square, okay, this will be h divided by the initial distance, let's call this d, where d is the expectation of x naught minus psi squared. Yeah, this is not right. You have to put the opposite. Yeah, that's correct. Okay, so if you just, I mean, it's just you try to minimize the right-hand side with respect to alpha, and it's a simple quadratic equation that you have to solve. And if you solve it, that's what you get. With the numbers that I'm not writing because I will certainly mess it up now, and I don't have them written on my screen. But the basic idea, as you see, is this trade-off. In order to get, if your d is large, if your distance from the initial point is large, then you want to have a large alpha. If your variance is large, then you want to have a small alpha. And this is the compromise. And this compromise is sitting at the boundary of the conditions imposed by the Robbins-Monroe algorithm. So you see, it's just at one of the two boundaries for my choice. Robbins-Monroe actually excludes it, but Robbins-Monroe wants to achieve something stronger than this second part, in which I have a fixed time horizon. But this is another way of looking at the theorem from another angle, which shows you exactly what this kind of scheduling is trying to accomplish. Move fast away from your initial point, and then slow down close to the target in order to kill the variance. Okay? This is a good way of balancing exploration with exploitation. Fine. Any questions so far? Okay. As a side exercise, this is one remark that I'm not going to give it to you, but those of you who are interested, if you make additional assumptions on the function, okay, so if you assume, for instance, that you remember there was an assumption on f prime. If you make further assumptions, something like f second, let me make it properly. Yeah, if f, sorry, that's not the statement. If you ask f to be concave, okay, so decreasing and concave, you can make this convergence even faster. Okay, but the price to pay is that you have to make assumptions over the function. Okay, so this is just to tell you that this trade-off may be balanced depending on how much you know about the function. Okay, I do not have time to go through this, but if you're interested, I can give you references. All right, because now what we want to do to close is just 2 steps. So first is to go to the multidimensional phase. Okay. So this is contained in a paper by Bloom of 1954. Okay, so this is also classical stuff. But I want you just a little bit to reason about what the problem becomes, and because this is important when you want to apply this to the value function. Okay, remember this is our final goal. So what, for instance, in 2 dimensions, okay? So if you have just 2 dimensions, what does this problem become? Well, suppose that we have now 2 variables, x1 and x2, and we must have 2 functions. Okay, so we have a function f1 of our variables x1 and x2, and the function f2, the same variables, and we want to set them both to 0. So we have a system of equations. Graphically, what does that mean? Okay, so let's say that the f1 function is in green and the f2 function is in yellow. Okay, so the level lines of the f2 functions, for instance, are lines like this. And the level lines of the green function are something like this. And one of these level lines, this one is f1 equals 0. And for instance, this one is f2 equals 0. Okay, so think about these 2 f1 and f2 functions as some very smooth function which have a definite direction in which they decrease. And what we aim at, and we want to identify the point here, which is the solution of these 2 equations. And of course, we have to assume that these 2 functions are in a sense linearly independent, in the sense that their level lines don't overlap, and etc. So let's assume all these nice things happen. Then the question is, how do I find the green point? Again, if you have no noise, you just do the same thing. So you try to go down the level lines of both functions. Okay. But now we are interested in a slightly more difficult version of the problem. Okay. Because when we go from 1 dimension to many dimensions, we could formulate our problem in different ways, but only one of these is relevant for the problem of learning the value function. So explicitly, let's think again about the problem of the oracle. So suppose now you choose a point x1, x2, okay, any point here, and you're going to ask me, give me the values of the function f1 and f2, and I tell you, no, that's not going to be the rules of the game. The rules of the game are, you can ask me one of these 2 functions at a time. I can only give you one of them. It's slightly more difficult, okay? But the bottom line is that you can do this thing as well in this case. So the way you do it is basically, okay, you are going to give me function 1, and then I'm going to go down along function 1. And if you give me function 2, well, fine. I'll do a step like that. Okay. So there is clearly a way out also in this situation. What is less intuitive is that actually this solution of going steps along the directions is not necessary. Even if I give you only the function 1 at one time, you could decide to take a step in this direction, which is slightly more subtle, okay? But it's something which turns out to be important in temporal difference learning, okay? So for the moment, just take it as a remark, a side remark. I hope tomorrow in the tutorial it will become clear what I mean. So the bottom line of this is that even if you add the stochasticity, that is, if you have noisy estimates of your functions, f1 and f2, the one that I give you, you will be able to reach with probability 1 this target as well. And this is what the math tells you if you formulate the multidimensional problem properly. Okay, we don't go through that, but you should have the means to understand what is contained in such a demonstration if you want to, in such proofs if you want to go through. Okay, so because what I care the most about now is that we go back to learning the value function. Okay, so let's just schematically recap what the analogies are. Okay, so this is going to be now a table of analogies between the simple situation we've been discussing and the language of temporal difference learning, that is function approximation, stochastic approximation for the value function. So what is the zero that we are looking for in this multidimensional version, okay, which is this point here? What is it? Well, the correspondence is that this is the value function of my given policy, which is a vector. Okay? So the zero I'm looking for is the value function. So what is the equation that this obeys to? Well, this is just the recursion equation, which in full, I recall you, is just like sum over A S prime So this is the recursion equation, and clearly is a set of linear equations which have to be satisfied by my value function. But of course, what does it mean to know my f? It means to know my p and my r, which is exactly the problem that we want to face. So we have to move on. And what are the phi's then? What is my random function? Well, my random function, whose expectation is this recursion relationship? Okay, remember phi of x was the object which was defined in such a way that expectation of phi of x was equal to my function f of x. So what is this? Well, this is the temporal difference error that I introduced last time, which is the reward minus a generic vector d at st plus 1 minus, sorry, plus gamma minus b at st. And my guess x at any time t will be some vector estimate for my value, which I put here. So you see, this is the table of correspondence. Any point x, which is my guess, is one estimate of the value function. The true value function that I'm looking for is the solution of the recursion equation, which is the value of the policy that I'm currently investigating. Okay, so this is the correspondence between the things that we've been playing with so far and the things we're after. So when we summarize all these things and we put everything together, we get our temporal difference learning algorithm, okay, which, since we are in many dimensions, now I'm going to formulate in this flavor. Okay, so we take a step along any of these functions that we have gotten. Why do we get just one function at a time in temporal difference learning? Because at every step, we are in one single state. Every time that we move along our process, we visit one state at a time. We do not visit many states at a time. So we have just a sample of this vector along the component which corresponds to the current state. Is that clear? So think about, let's make a quick example. We have time for this. Suppose, for instance, you have a two-state model, a two-state MDP. Okay, and state 1 and state 2. So, and the policy is fixed. Say policy, e.g., random. Doesn't matter. How do we learn the value of this policy? Well, we start and we pick up one state, S1, S equals 1. Apply the action, and then you might end up again in 1 or in 2. And at each time step, you can measure this temporal difference error. But you measure it only from the state you started and to the state you arrived. So of this vector here, you're sampling just one component at a time, the one which belongs to the value function you have, right? So in the space of value functions, component 1, component 2, here somewhere is your 0, which is my value of the policy, the true value. Okay, this is similar to this picture here. Same thing here, only for value functions. And I start somewhere here. So this is my first guess. Then I am observing the temporal difference error, which is a scalar quantity. It's a number. From the state here 1, maybe to the same state 1. So, and now what step do I take? Well, in the simplest implementation, I was in state 1. Well, I'm going to take a step along the 1 axis. Now, at the second step, am I still in state 1? If yes, I still move in this direction according to the error. Now I jump to state 2. Okay, I'll make a jump here. Okay. And so by this moving along the axis, I can mathematically show, which I will not, that this nonetheless converges to the point. Okay, so I'm ready to formulate the first final point of our procedures, that I'm going to define an object which is called the temporal difference 0 algorithm. And then later I will explain why there's a 0 here, which works as follows. Basically, choose an estimate V naught. Okay, at the beginning you start with an estimate for the value of your function. Could be all zeros. Okay, you don't expect anything to happen for you with any policy you choose, and then you set everything to 0, or you choose random numbers. Doesn't matter. Okay, fortunately enough, the problem is convex in the sense that it's a linear problem with contracting objects that play on it. Okay, this is not Bellman. Remember, it's a linear problem. No, nevertheless, it is contracting because gamma is less than 1. So it's a safe problem from the viewpoint of finding stuff. So it doesn't matter where you start. If you start with a good guess, you get close faster to the solution. If you start with a bad guess, it will take longer. So choose this and then repeat the following steps. Your next guess at step t+1 of the full vector, component by component, is your previous guess plus the learning rate, the learning steps, which you schedule according to Robbins-Monroe, the temporal difference error, and then look here, this is a scalar. Now here you have to choose in which direction you want to move. And this rule of going along the axis, depending on what you visit, tells you that here, this should be 1 if your state, you are in the state that you are just visiting. So of your vector, you just change the entry which belongs to the state you have just visited. Then you move to another state, you sample the error, and you check, okay? Where I recall you once more that the temporal difference error for completeness, this is okay. So you have a guess, which is your vector of values. From this, you observe the new reward, and you construct the temporal difference error, which I recall you is the difference between the reward that you observe and the one that you would have predicted according to your approximated value function. If there is a discrepancy, then you adjust your new value according to that. That's it. Okay, so this algorithm is the simplest way of performing learning of a value function. It is way more efficient than Monte Carlo. Okay, because you're leveraging on the fact that you accumulate your learning. You start with a guess, which technically is called bootstrapping. Okay, and you improve your guess. You start from somewhere, you bootstrap from some choice, and then you use this bootstrapping in order to improve. Monte Carlo does not do bootstrapping. It just samples. Of course, bootstrapping introduces a bias, which depends on your guess. If your guess is good, the bias will be low. If your guess is bad, there will be more bias. But the scheduling of the rates according to Robbins-Monroe takes care of this and balances this variance and bias. Okay, is the general picture clear? Of course, the details require a little bit of care, but it's very straightforward to implement. And tomorrow you will see this in action. Okay, so we will write down Python codes with Emanuele, which learn the value function in some simple MDP. Okay. Final remark. Why is this TD 0? Well, it's called TD 0 because, in fact, a more general form you could write the update as follows. So as a vector, okay, so this is a more formal writing, not in component. You could write this, the new vector, the new approximation for the value function is the previous one plus the learning rate plus the temporal difference error. This is always there. Okay, so this is always present. And now here you put something else. So this is a vector, okay? And this vector is called the eligibility vector. So in the case of TD0, it's just a vector which has all zeros and one in correspondence to the entry that you've just visited. But in general, it could be any vector. What does it mean in geometrical terms? It means that it's not necessary to take a step along the axis. Even though you sample along one particular component, there is a way to take steps which move in diagonal. You can do that. And this is what this eligibility vector is doing. Of course, you cannot do things at random, okay? But you have to do it according to some rule. What is the idea behind this rule? Well, what you're doing here with this eligibility vector is that you are assigning credit two states. Okay, so this is where the credit assignment takes place. So what does it mean in practice? Let's go back to this picture. You had a guess. You check this guess against reality. That is, you measure your reward and you compare it with what you were expecting based on your guess. Now it turns out that, for instance, you get a positive temporal difference error, which means that you are positively surprised. You were expecting less, but you have seen more. Now you have to sort of update your value function. And you ask the question, okay, I have seen something which was better than before, but which state do I have to credit for this? In TD0, you credit just the last state you visited. Okay, you say, okay, everything that is happening now, the good and bad things that I see, just depend on what I just did, or where I just was. And this clearly is limiting, okay? It's not wrong, but it's limiting. You might want to find other choices. For instance, maybe the responsibility of what is happening now is not just what happened at the previous step. Maybe it depends on 2 steps back, on 3 steps back. So you can incorporate this notion of credit assignment. So to give credit to states that you have visited in the past for the improvement that you're receiving now during the learning, okay, in a better way. And this better way leads to a class of algorithms which are called TD lambda algorithms, where this lambda is actually a measure of the memory of the states that you've visited in the past. Okay, so TD0 means that basically you don't blame or you don't give positive credit to what happened except from the very last step in your visiting around the states. But with lambda, you go back in the future. Yeah, sorry, you go. Yeah. Okay, it's complicated. So there is both. There are both backwards and forwards interpretation of TD lambda. I am mixing the two. So I want to say you go back in the past to give credit. Okay. And what is interesting is that when lambda approaches 1, this becomes Monte Carlo. Okay. So in a sense, this class of algorithms encompasses the full spread between strong bootstrap in TD node and no bootstrap at all in TD1. Okay, so we will have no time at all to go through this with the proofs. Good news is that everything is explained very clearly in the Sutton and Bartow. So if you want to go through that, given the background, it should be an easy read. Okay. Second good news is that tomorrow, Emanuele will give you examples. So seeing how it works in practice, you can get a sense of what it means. Okay. Third good news is that all these concepts, temporal difference error, eligibility traces, have neural correlates in our brain. Okay. So there exist things in our brain like dopamine signaling and many others, neurotransmitters, the way cells fire, which are, I wouldn't dare to say exact, but extremely close biological implementation of the concepts of the algorithms that we discuss here. Okay. Fourth bad news is that, sorry, your students, you have to do a lot of work to get all the math that's behind all these things. Okay, so if you want to delve deeper, we cannot do this in these classes, but I can point you to references. And the Sutton and Bartow is a very good book for all these references to neuroscience, to psychology, to operant conditioning and conditioning. So I invite you to take a deep dive into the book for all the things that I'm not able to cover. Okay. So plan is tomorrow tutorial with the things happening for real, and from next week we go back to our original goal, which is to merge learning with control. Okay, this part was learning to predict, and then we learn to predict to control. And okay, I think I'm done, but happy to take questions if you have. Okay. If not, have a nice day and see you tomorrow at 9.
Thank you. Goodbye.
Bye.
Thank you.
Bye. See you tomorrow.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.